In today's lesson, we're going to recap a little bit about theoretical and experimental probability, as well as talking about the complementary rule, some probability dealing with permutations and combinations, as well as, lastly, geometric probability. So bits and pieces are going to be some review from Algebra 2, but there's going to be some newer material in today's lesson. So today's lesson's on lesson 11.2. And we start off with some vocabulary words. So if you notice on your note sheet, you guys can start filling out some of these definitions. But basically, probability is the measure of how likely an event will occur. And the outcome is the possible result of the probability experiment or situation. So for instance, flipping a coin, your outcomes there would be a heads or tails. That's usually listed as a sample space down below. So it says sample space is the set of all possible outcomes. So if we did flip tail, our sample space would be heads, comma, tails. If we rolled one dice, our sample space would be 1, 2, 3, 4, 5, and a 6. Other things we'll see is like cards, drawing cards, or maybe beads out of a bag, that kind of stuff. But the event of the is an outcome or set of the outcomes. And so usually we describe that as probability with parentheses of event. So if I'm flipping a coin and I want to know how many heads I got, then we do probability of heads in parentheses, just like that. With probability, if you remember from Algebra 2, basically we can have a 0% probability or all the way up to 100% probability, which is going to happen. Equally likely outcomes have the same chance of occurring, and favorable outcomes are the outcomes we want in the given event. So this leads us to the formula for theoretical probability. In fact, we say the probability of any event occurs, and you can record this in the box there on your note sheet, is the number of favorable outcomes in the event over the number of outcomes in the entire sample space. So here it says, imagine you toss the same coin 20 times. What could you expect to land on heads? Well, since there's only two sides to the coins, we would expect 50% probability there. So we would expect probably a 10 out of 20, which reduces to 1 over 2. We can describe probability as fractions or percentages. So we'd say 50% probability, or decimals, 0.5 probability. So let's take a look at this example here. It says you roll 2 dice. What's the probability that you roll double, roll a sum of 6, or roll some more than 8? So here we have the sample space right below us. So if you notice, first thing we're going to do is find the probability of double. We got to figure out how many are in the sample space. Well, if you roll 2 dice, 6 options on top, 6 options on the second dice, we have a total of 36 possible outcomes. So that's in our sample space there. Rolling a double, if we circle all the doubles in our sample space, that would be a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and a 6, 6. That looks like there's 6 total out of 36, and we do expect you to reduce your fractions. So 6 out of 36 becomes a 1 out of 6 probability. So now if we roll a sum of 6, let's circle all those options. Well, let's see. I guess we could get a 1 and a 5, a 4 and a 2, a 3 and a 3, 2 and a 4, 1 and a 5. You can kind of notice a lot of your outcomes end up being the diagonals of your sample space. So here we only have 5 total options out of 36. We cannot reduce this fraction, so that stays as 5 out of 36. Now the last one, more than 8 would have to be a sum of 9, 10, 11, or the biggest sum we can get rolling 2 dice is 12, 6 and a 6. So let's circle all those cases that are sums of 9 or more. So that'll be 9, 6, 3, 5, 4, 4, 5, 3, 6. Also all of these. So if you notice, it's sort of the bottom right corner of our sample space. And if I count all those up, looks like I get 10 total. So it'd be 10 out of 36, and that can be reduced to 5 out of 18 chance. Next, this leads us to what's called the complementary rule. Complementary rule is basically the probability that it doesn't happen. So if we find the probability of when it happens, we can just do 1 minus that probability, because remember, all the probability adds up to 100%. So if you do 1 minus the percentage or fraction of that probability, that will be the probability of it not happening. So if you notice in this case, we're flipping 2 coins. If I flip 2 coins, my sample space would be heads, heads. Both of them could be heads. The first one heads, the second one tails. I could have the first one tails, second one heads, or really both of them being tails. So there's 4 different options when you flip 2 coins. So it says, what's the probability of flipping 2 heads? Well, that would be only 1 out of those 4. What's the probability that you don't flip 2 heads? Well, if you notice in our sample space, that's the other 3 out of 4. But how we can get that also is using the complement rule. 1 minus it happening would give us 3/4 as well. So now if you flip over your note sheet, we're going to kind of finish the lesson talking about experimental probability, some probability involving permutations and combinations, as well as lastly, some geometric probability questions. First off, the definition of experimental probability you can write at the top of your note sheet is the probabilities that are calculated based on the results of an experiment. I could flip a coin 100 times, and experimentally, if I flip it 100 times, experimentally I could come up with 20 being tails and 80 being heads. Now, is that likely to happen? Probably not. I would probably see more of a 50 tails, 50 heads around there, or maybe it's not exactly, but 47 tails, 53 heads. That's what we can expect theoretically, is about 50-50, but experimentally that could happen in an experiment. So we set it up the same, where we do the number of times in the event over the number of possible trials in this case. So sometimes you have to figure out how many trials there are, or sometimes in the word problem it actually tells you how many trials there are. If you notice the example on the side here, we have 100 tosses and an oddly shaped number cube. Find the probability of each of these. So if you notice, it does tell us it's 100. If we didn't have that, we'd have to really count the heights of all our bars here to figure out how many trials there are. But what's nice is that we have it in front of us. So here we need to find, looks like probability of rolling a 3. Well, notice rolling a 3 is slightly above 15, so I'm assuming that's 16. So it would be a 16 out of 100 chance, and that does reduce to 4 out of 25. Rolling an even number, well, rolling an even number would be a 2, 4, and a 6, and it looks like we have about 21 2s. Looks like we have about 11 4s, and then that 6 looks to be about on 12. So if I add all those up, it looks like I get 44, so it would be a 44 out of 100, and that reduces also to, if you divide by 4 from each top and bottom, looks like we get 11 out of 25 chance there. Rolling a number other than 5, let's do the complementary rule here. Let's figure out what it is for 5. So if I read the top of the bar of 5, that looks to be probably about 23, it looks like. So if 23 out of the 100 are rolling a 5, then if we do 1 minus that, that's going to give us the complement, aka other than 5. So if I do 1 minus that, that ends up being 77 out of 100, and we cannot reduce that number. So about a 77% chance of that happening. So now we get to some of the more difficult part here. This is kind of the newer things. Probability involving what's called permutations or combinations. We did permutations and combinations yesterday, but these are some questions dealing with sort of those permutation and combination outcomes there. So we have some steps for you to follow. If you want to record these on your note sheet, you can pause the video here and record these down. But the very first step is to determine whether or not the problem involves a combination or permutation. So think order, does it matter or not? Combination, remember we're looking for those keywords of select and choose. Permutations, we're looking for those keywords of arranging or ordering things, right? But the second step is you're going to calculate the number of possible outcomes using those permutations or combinations. That's going to be what it's going to be out of. So in the second step, you're kind of finding either permutation or combination, but that's going to be our sample space here. And then you have to think about what the number of favorable outcomes in the event is. Is it 2? Is it 1 of them? Is it only maybe 3 options that it could happen? But you take that number and divide it by how many you got in step 2, and then that will be our answer for our probability. So we're going to take a look at two word problems here, one involving a DJ on your note sheet and the other one involving a clerk. So here it says a DJ randomly selects 2 of 8 ads to play before her show. 2 of the ads are by a local retailer. What is the probability that she will play both of the retailer's ads before her show? So the first step is we need to think, is this a permutation or a combination? Notice there is a keyword, selecting 2 of 8. It doesn't matter the order of the 2, but they're selecting 2 of the 8. So here order doesn't matter, so this would definitely be a combination setup. So our setup would be 8C2. And if you do this on your calculator, you'll see that we get 28. So we know our probability is going to be out of 28 total possible ways you can select 2 out of the 8 ads. Now it says 2 of the ads of the retailer are local. What's the probability that she'll play both of these ads before her show? Since 2 of the ads are local and you're playing 2, then there's only one scenario we can have that they play both of those ads. And so that would be simply a 1 out of 28 probability of happening. Let's take a look at the next one here. So I want you guys to try this one on your own. First step is to think, is it a combination or is it a permutation type problem? Once you know what it's out of, think about the scenario of 4 letters being placed out of the 4 different letters, right? There's only one scenario there. So see if you can come up with your right probability. You can pause the video, try this one out, and we'll go over this here in a second. So notice here it says 4 different letters need to go into 4 different envelopes, so that's pretty specific. Order does matter here. So this is definitely a permutation setup. Notice we have 4 letters and we're trying to order them or arrange them into 4 different envelopes. So the setup would be 4P4. And if you do this on your calculator, you'll see you get 24 total options there. So we know it's going to be out of 24. And this one's similar to the last one where the probability of 4 letters being placed in the correct envelope, so that's only one scenario here. Now if we were only thinking 2 of the 4 being placed, then that would be a sort of a combination on top. Where would you put? But since we're doing 4 and we're choosing 4, 4C4 ends up being 1 total possible scenario, so it's a 1 out of 24 chance of that happening. For the last objective, we're going to take a look at geometric probability. So this is landing in the shaded area, or whatever area we're pertaining to. The setup here, if you want to record this in your box, is simply the area of the region we want divided by the entire area region itself. So if we take a look at this problem here, it says if a circle has a radius of 10 centimeters, so I'm going to draw this out, 10 centimeters, placed inside a square with a length of 20, what's the probability of landing inside the circle? So in this case, our entire region is going to be the outside square. That is our whole surface area we have to deal with. And so it's going to be out of the area of the square, which we know a square is 20 times 20 here, so it'll be 20 squared on the bottom. Over the, looks like the top part's going to be the shaded area, that's what we want to land on, and that's the area of the circle. And the area of the circle we use is pi r squared. Since the radius is 10 here, our setup on top would be pi times 10 squared. So if I simplify this, I get 100 pi divided by 400. We can use our calculator now to figure out the percent of that happening, or the fraction that it could be, but this one's going to be a little difficult because we have pi involved, so we're only going to come up with the decimal or percent here. So if you do this on your calculator, you're going to end up getting 0.785 as a decimal, and so that's about a 78.5% chance of that happening. So let's take a look at a few more here together. It looks like we got one more to try on together, and then one to try on your own here. So here it says, find the probability that a point chosen at random will fall inside the circle but outside the triangle. So there's sort of a miscolored hue here around the circle, but we're only kind of worried about the circle here, so disregard that yellowish square that's around it. That just happens to be the image that was pulled in here. So we're only focused on the circle. So remember our setup's going to be, looks like our whole image is going to be area of circle over, I guess in this case it's going to be area, we're not worried about the triangle here, we're worried about sort of landing in the white area. So in this case we have to take the area of the circle and subtract it off the area of the triangle. That's going to give us that remaining area inside the image. If it was just simply the shaded area we're worried about, well then it would be the area of the triangle over the area of the circle. But in this case it's the remaining space between those images. So we have to subtract the two on top. Area of the circle, again, pi r squared. If you notice the image, this whole length is 8, so that means the radius of the circle is going to be 4. So we know it's going to be pi times 4 squared on the bottom. That's the whole area outside. And we can copy that over for the top part here, because the area of the circle we're going to need to be able to find the remaining space. So we have to subtract off the area of the triangle. A triangle area, remember, has 1/2 base times height we use. Notice the height ends up being the radius as well, and the base is 4 here. So we're going to subtract off 1/2. My base is 8, my height is 4. This would be our setup. Now when you're doing this on your calculator, I would highly encourage you kind of doing the top part first, writing that answer down. So if you do that on top, you're going to get a decimal of 34 point, looks like 265 something, divided by, I guess, 16 pi. And so when you're doing this on your calculator, make sure you group 16 pi in parentheses, because a lot of students will mistakenly not do that and it will accidentally read it as multiplying by pi at the end. So we want to group that. So our final answer would be 34.265 divided by, in parentheses, 16 pi. So we get an answer of 0.682, and so it would be a 68.2% chance of that happening. So here's one that I want you guys to try on your own. It's a shuffleboard game. We have the dimensions here, so let's label those out, and this is on your note sheet as well. It says the length of the rectangle is 10 feet, so I'm going to label that as the longest side, and then the width of the orange rectangle is 5. The blue one inside is slightly smaller, so the length there is 4.2, and the width there is 3.5. This one's asking you what's the probability of landing in the orange area. So remember, the orange area is kind of the outside area, so it's going to be similar to our last example that you got to subtract out that blue area on top. But I want to see if you guys can try to set this up on your own and get to the correct probability. So pause the video, try this one, and we'll go over this here in a few seconds. Good luck. So if you notice, the whole image, what it's going to be out of is the entire big rectangle, which is the orange one itself, and that area is a 5 times 10, which ends up being 50 square feet. To find out the remaining area, we have to take the orange area and we have to subtract out the blue area. That's going to give us the remaining orange area total. We already have the orange area, so we just got to figure out the blue area. So if I do 4.2 on my calculator times 3.5, the blue area ends up being 14.7. So if I do this on my calculator, 50 minus 14.7 ends up giving me 35.3 out of 50. If I divide that by 50, looks like I get a 0.706 or 70.6% chance of that happening. So what I want you guys to know is go on Canvas, and I do want you to complete the homework quiz today. So try your best. Remember, you can take that multiple times until you get a 5 out of 5. And then don't forget to complete the practice as well. You can check the key that's posted on Canvas, or you can check the key in the front of the classroom. Have a great day.